now let's see how we can apply the comparison theorem for a problem, right? Now here we are asked to show that this integral is convergent. Now by observing this infinity in the upper limit, you can say that this is an improper integral of type 2. So the fundamental way of evaluating the convergence of this integral is to like manually calculate the integral of this one, right? And then we should get the limit, and if the limit is finite, we say that the integral is convergent. But the problem is, with the knowledge that we have on integration, we are not in a position to calculate the integral of this function. Okay, so that's the problem. Now there are some theories to prove that this function is integrable. That means there is an answer. We can prove that there is an answer, but we don't have a method to show the answer. Okay, yeah, I'm not going to discuss a lot on that topic, but here what is important for us is that now with the techniques that we have done so far, we cannot evaluate the answer of this integral. So we cannot use this limit conditions to evaluate the convergence. So what we do is we obtain a more simpler function so that we can compare it with this complicated term. Okay, so if we consider fx as e to the power negative x squared, we will have a different function so that we can compare it with fx. Then we can use the comparison theorem to obtain the convergence. And also this comparison should only be done for the x values in this range. Okay, so the x values, if we have a as the lower limit, the x values should be taken from a to infinity. Okay, we don't need to consider any x term, any x value which is not within this range of this interval. Okay, so this should only be true for the x values within this range. Okay, I forgot to mention that in the previous video, right? So now simply what we have to do is we need to, now as we have to show that this integral converges, what we need to do is we need to find a larger function so that the integral of this larger function within the same range converges. Okay, if it happens, then since this is larger than fx, then from the comparison test we can say that the integral of the smaller guy will also converges. But now we should figure out the suitable function to compare with e to the power negative x squared. And remember, this comparison should only be done within 1 to infinity. Okay, so you don't have to consider any value less than 1. Okay, right, so let's take gx as e to the power negative x. Okay, before doing the comparison, let's see whether it converges or diverges within this interval. Now this one, we know the answer for this integral, right? And since this is a type 1 integral, we can use the theory that we have done before. Okay, that means we can write down the integral like this, and then evaluate the answer, and it will be something like this. Okay, not something, but the exact answer is this one, right? So what you do is you write down the integral as a limit problem, and then evaluate this integral, which is equal to negative e to the power minus x, and by substituting the upper and lower limit you can obtain the answer as e to the power negative 1. In other words, our simpler function will converge. I mean, the integral of our simpler function will converge. Okay, so now if we can show that for x values in the given interval, for this x values, if we can show that fx is less than or equal to gx, and as we have proved that the integral of gx converges, then from the comparison test we can say that we have the convergence of fx as well. So now it's just a matter of proving this inequality between the two functions, and to do that we can see, since x is greater than or equal to 1, since x is greater than or equal to 1, we can say x squared is greater than or equal to x, right? Because if it is less than 1, then this inequality is the other way around. For example, if we have x equals 0.5, then x squared will be 0.025. okay, so no, not 0.025, it will be 0.25. okay, so here when x is less than 1, x squared is less than x. okay, but when x is greater than or equal to 1, we have this relationship. Therefore, when we multiply it with the negative term, then the inequality sign will change. So now here what we have is negative x squared is less than negative x. Then now you can see ex graph, ex function is a increasing function. okay, so whatever the value we have in the left is less than the value you have in the right. okay, no matter where it is located, if a is less than b, then e to the power a is less than e to the power b, because ex is an increasing function. No matter where this a and b are located, if you have this relationship, then you are going to have this relationship, because ex is increasing throughout. So accordingly, since ex is increasing, we can apply the same result as it was in here, right? So e to the power negative x squared will be less than or equal to e to the power negative x. In other words, this is the function that they have given, right? fx, and here we have the new function that we introduced. So for x values greater than or equal to 1, that is within this range, we have this relationship. And we proved that the integral of gx from 1 to infinity converges. okay, therefore by the comparison theorem, we can say the integral of the other function also converges. okay, right, now see what we have proved is the integral of 1 to infinity from 1 to infinity of the function negative x squared dx converges. Now if we draw the plot, okay, starting from, let's start from 0. Now for this function, what is the value of this function at 0? That means e to the power negative 0, and that is equal to 1. So it will start with 1. Okay, so if you plot it, it will go like this, right? And we have showed that the area in this region, okay, starting from 1 to infinity, is a finite value. Okay, so this area is a finite value, and since the function is continuous, and as you don't have any vertical asymptotes in between the region from 0 to 1, we can also say that this area is finite. Okay, that means taking both these facts into account, we can say that the area from 0 to infinity of ex squared is also finite. In other words, this integral will also converge. Now here we used several facts, right? Now in order to prove the convergence of 0 to infinity of this function, I mean convergence of this function within the range 0 to infinity, first we considered the same function from 1 to infinity, and to prove the convergence of 1 to infinity, we needed another function, a second function, because we were going to use the comparison test. And for this simpler function, to prove the convergence of this simpler function, we use the fundamental idea of convergence, that is by considering this limit. And keep in mind that we are evaluating it within 1 and infinity, and then for 1 and infinity of this integral, we saw that the integral converges. And for this same range, that is 1 to infinity, we saw that there is a relationship between the two functions, where this is the original function. And since the larger one converges, we can say from the comparison test or comparison theorem, both are the same, we can say that the original function from 1 to infinity converges. And by considering the fact that you don't have any vertical asymptotes in between 0 and 1, we can say that the area between 0 and 1 is also convergent, finite. So as a result, we can say the area between 0 and infinity of this function can be written as area from 0 to 1 plus area from 1 to infinity. Since both these integrals converges, we can say that the total integral, which is the integral of e to the power x squared from 0 to infinity, is convergent. Now you might have a problem here. Now you might get this doubt, why couldn't we do the comparison for this whole interval from 0 to infinity? Why couldn't we use the same function e to the power negative x and do it at once for this whole interval? Why couldn't we do that? The reason is, now see, in this calculation, to obtain the relationship between fx and gx, we use the fact that x is greater than or equal to 1. Okay, so only when this is true, you have this relationship between f and g. Otherwise, it is not. So, we cannot use the comparison test, right? See what will happen. Now, if x is less than 1, if x is less than 1, then x squared will be less than x, right? So, negative x squared will be less than negative x. In other words, negative x squared so by multiplying this one with negative sign, the inequality symbol will change. So negative x squared will be greater than negative x, right? Then if we just take this one 0 to 1, and if we have this one 0 to 1, and like infinity, wait, now see, even we cannot consider this complete interval, because from 0 to 1 we have the opposite direction of the inequality, but from 1 to infinity you have the other way. Okay, here ex squared is less, but here ex squared is greater. So that's the reason for not taking the complete range from 0 to infinity when evaluating the integral, or when evaluating the convergence of this integral. Okay, that's why we separated it into two regions, from 0 to 1 and 1 to infinity. And for 1 to infinity case, we use the comparison test, and from 0 to 1 case, we just make use of the fact that you have a finite area by looking at this diagram and taking into account that the function is continuous. That means it doesn't have any vertical asymptotes. So putting all these things together, we can say that the improper integral from 0 to negative infinity of e minus x squared converges. Now see, this is important because we did not know how to evaluate this integral, although even if it is a definite case, right? We did not know the answer for this integral, so we couldn't do it by the fundamental method, that is through limits, right? So that's why we use the comparison test. And finally we will do this one to show that this integral diverges. Now for this one also we use the comparison test. Otherwise, if you are going for the fundamental things, then we will need the limit of the 1 to t of 1 over x plus e minus x over x, and to find the integral of this one, it is difficult. Okay, so but simply what we can do is we can see that you have this relationship. You can write this one as e minus x plus x. Now see, e to the power something is always positive. Okay, so this number, and we know x is greater than or equal to 1 because we are considering this range. Okay, so this is a positive number and this is a positive number, so this term will always be positive. And here what we have is 1 over x plus a positive number. That means it is always greater than or equal to 1 over x. In fact, it's strictly greater than 1 over x, right? Because here we have 1 over x and here we have 1 over x plus something, plus some positive number. Okay, so it is definitely greater than 1 over x. Say for example, if we have 2 plus some, no matter how small it is, if it is a positive number, then it is definitely greater than the original starting number. Okay, and that means our original function is greater than 1 over x, and so we can use the comparison test like this. And we have already computed that this integral diverges. Remember, we even did a theorem saying that if we have x to the power p dx, then if p is less than or equal to 1, then the integral will diverge. So according to this theorem, we know that the smaller integral diverges. In other words, from the comparison test, we can say the larger integral will also diverges. Okay, so this will conclude the section 7.8.